Children diagnosed with autism and autism spectrum disorders struggle in social situations, they find communication a challenge, and they may have behavioural problems and often fall behind at school. At the moment, the diagnosis can only be made clinically, in other words, by a specialist assessing a child. There's currently no biochemical test for the condition, and that means most of these diagnoses tend to be made late, possibly missing an opportunity to intervene therapeutically at an earlier stage. Well, now that could be about to change. Jürgen Hahn from Rensselaer Polytechnic Institute in the US has compared blood samples collected from a group of autistic children with blood samples from unaffected volunteer controls, and he's found a signature change in a range of biochemical markers that are significantly different among the autistic patients.
Currently, approximately 1.5% of all children in the US and most other developed countries are diagnosed with autism spectrum disorder. The average age at which children get diagnosed with autism is 4 years. But there's general agreement that you can diagnose as at the age of 2, sometimes even as early as 18 months. However, performing an autism diagnosis is not simple. There is not a single test that you can actually use that really determines if somebody has autism or not. The way this currently works is that you go to a doctor, they perform an observation of you, and based upon this observation, they come up with a diagnosis.
But is autism not genetic? We know it runs in families, for example. So is there no genetic test that you could do to find people who might have it?
Autism has a strong genetic component. However, there is not a single genetic test that really will tell you if somebody has autism or not. There are a few genes where we know that they result in autism, but this is a very, very small percentage of all cases. We're talking less than 5%. So the vast majority of children that have autism, we don't know what genes are responsible for it. And we literally have a list of several hundred potential genes that may increase your risk of getting autism, but none of them are good enough to perform a diagnosis as of now.
So how are you trying to solve this?
What we are doing is that instead of looking at one marker at a time, we're looking essentially at multiple markers all at once and take that information into account, because it may very well be that somebody has one marker that by itself is not responsible, but in combination with a few others, it may very well be responsible.
And what sort of markers are we talking about here?
We are looking at compounds that the body produces that you can measure in blood or plasma samples.
Right, so I suppose if you have a certain genetic makeup, your body's going to have a certain biochemistry. There'll be certain levels of certain chemicals in the blood. And you're saying, instead of measuring genes that might be linked to autism, let's just measure the chemistry of the body and see if there's a profile that goes along with autism.
That's exactly right. I mean, the genes, they basically form a blueprint. What we are looking at is what the body produces from this blueprint.
And also, if you've got multiple different genes that might cause a condition, the end point is that they all cause the same change in your biochemistry. If you just test the biochemistry, you actually infer any of those changes in any of those genes that might underpin the condition.
That's correct.
So how did you approach this? What did you actually do?
We took data from studies that had already been run, so we did not need to run an entirely new study. And what we did is we performed an analysis that looks at multiple factors of what we're measuring in the blood, all simultaneously. And based upon that, we then try to determine, do we see certain patterns in certain compounds? Are there too much or too little in the group of people that was diagnosed with autism spectrum disorder versus the one that deemed neurotypical? And we found that there's a significant difference in the two.
And what compounds or chemicals biochemically were you considering, and how?
We were looking at compounds that have a variety of functions, but the most important ones are things that are responsible for the methylation of DNA and thereby the expression of genes, as well as compounds related to oxidative stress.
And why does this ultimately matter? Because if we can diagnose autism on the basis of a professional sitting down with a person, looking at how they behave and saying, yep, it looks like you have a form of autism, why do we need a biochemical test to back that up?
Well, there's several things that we are interested in. One is we do want to move forward the date at which autism first gets diagnosed. Having a test that supports the diagnosis would certainly allow us to basically move that date forward. It's generally acknowledged that the sooner autism is diagnosed, the sooner some type of intervention can start, which will ultimately result in better outcomes. Secondly, there is the hope that we may be able to actually determine before somebody shows a lot of symptoms that they may develop autism. That still needs to be verified, obviously, but that's certainly one of the hopes we have. And the third piece is if we're able to correlate these compounds with the behaviors, then there's hope that at least we know what direction to look into if we ever want to go down some type of biochemical intervention at some point in the future.
Jürgen Hahn, and with that test, 97.6% of autism cases can be picked up correctly. The study has just come out in the journal PLOS Computational Biology.